Hi folks, the soft dinosaur tissue is now under a new name, SoftServeDinosaur. Folks have asked me to do this again in high resolution, and so here you go. But feel free to contact us if you have any questions or comments. We look forward to hearing from you. And I'm looking at something very exciting. I'm looking at dinosaur bone in my dissecting microscope. This is bone that I have put through what's called a decalcification process, and I'm actually seeing the soft tissues left over after the bone mineral has been decalcified or taken away. This is very exciting, of course, because dinosaurs are supposed to have lived and died some 65 million years ago. And yet we still find soft tissues in their bones. This actually happens to be a Triceratops horn that we dug out of the Hells Creek Formation in Montana. So on this series of videos, you're going to see some very interesting information about the dig, about the bones that we found, and about the soft tissues that we're finding in them. Here now is a piece of Triceratops bone that has been decalcified, so all the bone minerals have been removed. You can see how many of the blood vessels are here. This white area here, this is soft tissue on top of these blood vessels. So the bone is very stiff because it's fossilized, but yet there's soft tissue in here. This is about 40 power under the dissecting microscope. As I move this, you can see these soft tissues waving back and forth in the liquid. So this is impossible for these soft tissues to be here if these bones are that old. This would all be gone. But here you see the matrix of blood vessels that have all been permineralized. They're all hard rock, and yet these white areas show all of the soft tissue that is still present here after decalcification. So this is an indication that these bones are very young and not even 20,000 years old, probably much younger than that. So here we've redone the experiment with the little lighter fixative, and we have a piece of biofilm pulled yet from another piece of Triceratops horn, and look at how stretchy this is. This is almost like taffy. And so these biofilms, where bacteria come and eat the Triceratops tissue, leave these films, and inside of here are pieces of Triceratops tissues that we're going to thin section and show you the actual cells of the Triceratops bone tissue, the soft remaining tissue that's in these bones. And we'll do that next under high magnification microscopy. Here you see a piece of Triceratops horn that was collected recently at the Hell Creek Formation in the Badlands of Montana. Soft tissue in dinosaur bones has been reported from Montana since the late 1990s into early 2000s. However, these tissues were found in a Triceratops femur. This example we're showing you here is a Triceratops horn. Now a femur is highly encapsulated, and so it's not surprising that some soft tissues would be found in the deep center of it. But a Triceratops horn is highly vascular, and so we did collect this horn, a 48-inch long horn, in the Badlands of Montana. We brought it back to the lab, and here we are investigating, looking for presence of soft tissues in it. Now this is a highly vascular bone that was exposed to the soil and water and ice and freezing and thawing and insects and plant roots and fungal bodies and all manner of organisms trying to decompose this. And so the finding of soft tissues in this Triceratops horn is staggering. And the reason we're showing this is because few people realize it. We creationists wanted to go out and mount our own expedition and find our own samples so that we could publish widely on this, and we have. We published all of this in Acta Histochemica. In fact, it cost me my job at a state university in California, California State University, Northridge. Now this has major implications for the age of Earth and fossils. If soft tissues in dinosaur bones are the norm, and that is what we are predicting, then these bones cannot be 65 million years old because they're loaded with soft tissues. These break down quickly, and so they can't be old at all. A scanning electron microscope allows us to examine the exterior surfaces of specimens at very high magnification and resolution. This is possible because we're using electrons instead of light. Here you see the gold-coated specimen attached to a stub, which is now being attached to the specimen holder. Once it is attached to the specimen holder, we can place it inside the chamber. The chamber is a vacuum chamber, and it must be pumped down by vacuum pumps in order that all the ambient air, all the air molecules like CO2 and O2 and All the other molecules can be evacuated or taken out of the chamber so that the electrons won't impact any molecules on their way to scanning the specimen. Now the microscope is ready for us to image this specimen at high magnification and high resolution. Now what you see is a captured digital photograph off the scanning electron microscope. And at this low magnification, 30 power, we're seeing very clearly all of the blood vessels from this porous horn that was from the Triceratops head. Now this bone went through what's called a decalcification process. And so when we put it in the decalcification solution, it dissolves away all the bone minerals. So all these long dark areas in here, that's where the bone mineral has been completely dissolved away. And so what we're left with are these individual blood vessels that bifurcate or split and split again and go through this horn like roots through soil. Here you see a long bone, a T-Rex femur that Dr. Schweitzer collected in Montana. Parts of that femur were broken apart and put in a decalcification solution, and here you see the soft tissues that resulted from that. Some of these soft tissues had red coloring in them, and so it was suspected that it had blood products. And here you see the tissue with red blood cells inside the tissue, which astounded the scientific community. She further showed pictures of separate blood vessels with red blood cells and other products inside of them. And now you see the osteocytes that she recovered from the decalcification solution. These were individual osteocytes that were floating in her solution, and you can see them as distinct individual cells. Now bear in mind what Dr. Schweitzer found were individual osteocytes floating in solution in the decalcification solution after she completed her decalcification. What we found are sheets of tissue with osteocytes in them. This machine is a cryostat, or a frozen section machine, that allows us to freeze our tissues inside this chamber, and once they're frozen, we can thin section them to a very thin slice, about 10 microns in thickness. The silver specimen holder is at the center of the field of view here. I'm going to be placing specimens on it. These are specimens from the iDino project, thin films of tissue from the bones that we recovered. Once these are frozen, I can then thin section them to about 10 microns in thickness. And 10 microns is about 1/10 the diameter of a human hair. So now we're going to take the specimen holder. You can see the specimens embedded in them frozen material. We're going to load it into the chuck. Now we have to align the chuck to the knife, and in order to do that we have to create what's called a cutting window. Once the cutting window has been established, top and bottom, we can then advance the specimen to the knife, and now we can start making thin sections. And here you see me scraping off thin sections onto the stage. I'm going to lift the stage away, and with a slide I'm going to pick up those 4 sections right onto the slide, and that's what we're going to use to examine under the microscope after we stain it and cover slip it. Now I'm going to quickly show you some of these thin sections under the microscope. You can see the tiny little osteocytes in them. Sorry this goes so quickly, but I'm using antiquated equipment to film this. But look at these pieces of tissue full of osteocytes. These are all the little bone cells that maintain, manufacture, and produce bone. And so this is direct evidence of osteocytes in dinosaur bone collected from the Hell Creek Formation in Montana. Now I also use a scanning electron microscope, and here you see under the scanning electron microscope some images of cells. These are individual osteocytes under the electron microscope. Look at the delicate filopodia, or little tendrils coming off of them. These things should not be there if they're 65 million years old. Thanks a lot for watching, folks, and please share this with your friends. We want to get the word out about soft tissue and dinosaur bones. Also, please subscribe to our new YouTube channel, Backyard Microscope, where you will see more examples of soft tissue and dinosaur bones, new discoveries that we've made, and also all manner of things under the microscope. So thanks for watching and take care.